In this video, we will talk about contiguous memory allocation. Main memory must support both operating system and user processes. So the operating system can allocate the limited memory resource efficiently to multiple user processes. Operating system or kernel always reside in the memory. Normally, the kernel or the operating system are placed in the high address. For the contiguous memory allocation, each process is contained in single section of memory that is contiguous to the section containing the next process. Now, in this example, the memory space from the address 420,940 to 880,000, this contiguous memory space is allocated to this process. And this memory space or this block of memory space is contiguous to the memory space allocated to this process. This process can use the memory space from the address 300,040 to 420,940. Can use this memory space. Okay. Now for the contiguous memory allocation, we need to protect the memory space. Here we use the relocation register and the limit register. We use these two registers to protect user processes from each other and also protect user process from changing the operating system and data. This method, this memory protection method is very similar to the memory protection method we talked about in the background knowledge. The relocation register contains the value of the smallest physical address. The limit register contains the range of logical address. Each logical address must fall within the range of specified by the limit register. When a process is selected and dispatched to run on the CPU, the dispatcher loads the relocation and the limit register with the correct value as a part of context switch. Now, what is the correct value? Now, when a process is dispatched around the CPU, during the context switch, the smallest physical address is loaded in the relocation register. And the range of the logical address or the maximum logical address is loaded in the limit register. And the MMU, the memory management unit, maps the logical addresses to physical addresses by adding the logical address to the relocation register. Okay, now the CPU generates a logical address. This is the MMU, the memory management unit. It contains the two registers, limit register and the relocation register. First, the MMU will compare the logical address with the value in the limit register. If this logical address is greater than the value of limit register, means this logical address is outside of the range of the logical address space. So if this is no, that means this logical address is not legal. It's not a valid address. It causes a trap in the operating system. Now, if the logical address is less than the limit register, and then this logical address is added to the relocation register, This is the smallest physical address assigned to this process. So at the logical address and the relocation register value, we get the physical address. Now the CPU will use this physical address to access the physical memory to fetch the instruction or the data. Now one of the simplest memory allocation method is to assign processes to variably sized partitions in memory. Each partition contains exactly one process. The operating system keeps a table. This table shows which part of memory are available and which part of memory space are occupied by processes. Initially, the entire memory space are available. Here, the available memory space is called a hole. So initially, we have the entire memory space are available. So we have a very large hole. And with the processes are created and loaded in the memory and the processes terminate, release this memory space, we have the multiple or the set of variably sized hole scattered throughout the memory. When a process arrives or when a process is loaded in the memory, operating system takes into account the memory requirements of the process and the amount of available memory space to determine which hole is allocated to this process. The operating system needs to select a suitable hole for this process. When a process arrives, operating system search the set of variably sized holes that are large enough for the process. If the hole is too large, the operating system split this hole into two parts. One part is allocated to the process, and the other is returned to the set of holes. So this hole is a smaller hole added in the set of the holes. When a process terminates, this process releases the memory space allocated to it. The released memory space is placed back in the set of holes. If this new hole is adjacent to other holes, these adjacent holes are merged together to form a larger hole. Now, this is a memory allocation example, a simple example. Now, the current state is this. We have the operating system reset at the high memory and three user processes, process 5, 8, and 2. The process 8 terminates. The memory space allocated to process 8 is released. Now we have a hole here. These memory space are available. So we call it a hole. And then the process 9 arrives. Now this hole is split into two parts. This part is allocated to process 9. Now we get a smaller hole here in the memory. And then the process 5 arrives. Now the process 5 terminates. The memory space allocated to process 5 is released. Now we have this hole here. This hole, and now we have two holes scattered throughout the memory. Okay. Now, if the process 2 terminates, process 2 will release the memory space allocated to it. Now we have the hole 1, hole 2, and hole 3. Now the hole 2 and the hole 3 they're adjacent. So these two adjacent holes will be merged together, and we get the larger hole. The hole 2. The hole 2 is larger than these two smaller holes. So we have the different memory allocation strategies. So 3 memory allocation strategies. Given a list of variable sized hole and a process request n bytes of memory space. Now we have the first fit strategy, best fit strategy, and worst fit strategy. Best fit allocation strategy allocates the first hole that is big enough to the process. And the best fit allocate the smallest hole that is big enough to the process. But for the best fit must search entire list of holes, find the smallest hole that is large enough, unless the holes are ordered by size. The best fit produces the smallest leftover hole. And the worst fit strategy allocates the largest hole that is big enough for this to the process. Also, the worst fit must search the entire list of holes to find the largest hole, unless the holes are ordered by size. Worst fit produces the largest leftover hole. The experimental shows the first fit and best fit are better than worst fit in terms of access speed and the storage utilization. And now let's take a look at example of these allocation strategies. In this example, we have 6 variably sized holes. The hole of this with the 300 kilobyte, 600 kilobyte, 350 kilobyte, 200 kilobyte, and 750 kilobyte, and 125 kilobyte. 6 holes, they have different size. And now a new process, it requests 115 kilobyte memory space. This process will be loaded in the memory. And now the operating system need to allocate the memory space to this process. For the first fit strategy will allocate the first hole that is large enough. Now the first hole here in this example is a hole of size 300 KB. This hole is big enough for this process. So the 300 KB is larger than the 115 KB. So now this hole, the hole of the size 300 KB is split into 2 parts, 115 KB, and then the 300 minus 115 is a 185 KB. Now the 115 KB partition is allocated to the process. And now we have a hole of 185 KB. We get this hole. Now after the first fit allocate this memory space to the process, we have this, we get the hole. Now this hole changed to the 185 KB. This is the first fit. Now the best fit will allocate the smallest hole that is big enough. So now we need to search the entire list to find the smallest hole that is big enough. Now the 300 is big enough, but we're not sure if it is the smallest hole. Now the 600 is big enough for this process, but it's not the smallest. It's even larger than 300 holes. Now 350 big enough, but it's not the smallest one. 200 KB, this hole is big enough. It's so far it is the smallest hole that is big enough. And then the 750 KB, this hole is big enough, but it's not the smallest one. And then the last one is 125 KB. This hole is big enough for this process because the 125 KB is greater than 115 KB. And also this is the smallest hole in this list. So the best fit strategy will allocate this hole to the process. The hole of size 125 KB is split into two parts, 115 KB and 10 KB. The 115 KB partition is allocated to the process and leaving a hole of 10 KB. So now, because we use the smallest hole that is big enough, so the best fit leaves the smallest leftover hole, 10 KB. Now the worst fit strategy will allocate the largest hole that is big enough. Now, among these 6 holes, the largest hole is 750 KB. Now this hole is split into two parts, 115 KB and 635 KB. This 115 KB is allocated to the process, leaving a hole of 635 KB. So we see the worst fit strategy leave the largest leftover hole. Okay. This is a memory allocation, contiguous memory allocation strategies.